In this lecture, we discuss about the property of finite dimensional normed linear space, and we discuss some of the results in case of a finite dimensional normed linear space. So for this purpose, we need a lemma first. So let x1, x2, so on xn be a linearly independent set of vectors in a normed linear space X. Then there is a number c greater than 0 such that for every choice of scalars alpha 1, alpha 2, so on alpha n, we have norm of alpha 1 x1 plus norm of alpha n xn is greater than equal to b c times some modulus of alpha 1 plus so on alpha n, where c is greater than 0. Regarding the proof, take s is equal to b modulus of alpha 1 plus so on modulus of alpha n. If this s is equal to be 0, then all these alpha i's are 0. So that the given inequality holds for any c. So let s is greater than 0, then this inequality is equivalent to inequality which we obtained by dividing up this equation by a number s, which is equal to be modulus of alpha I summation over the I is equal to be 1 to n, and taking the beta i's is equal to be alpha i's over the s, such that the summation of this beta i's modulus is equal to be 1. That is, here we have taken up, by dividing up this term with respect to s, we get norm of a beta 1 x1 plus norm of a beta n xn is greater than equal to be c. So hence it suffices to prove the existence of a c greater than 0 such that the given inequality holds for every n tuples of scalars beta 1, beta 2, so on beta n, with summation of a beta i's is equal to be 1. Suppose that this supposition is false. So then there exists a sequence ym of vectors such that the ym is equal to be beta 1 m x1 so on beta n m xn, which is equal to the summation of a modulus of a beta ij xi, where the summation of a beta jm is equal to be 1, such that the norm of ym converges to be 0 as m converges to be infinity. So since we have this beta j's m is equal to be 1, we have modulus of beta j's m is less than equal to be 1. Hence for each fixed j, the sequence is bounded. And consequently, by the Bolzano-Weierstrass theorem, this sequence or bounded sequence has a convergent subsequence. So let Beta denote the limit of that subsequence, and suppose the subsequence y1m is equal to be gamma 1m x1 plus summation j2 to n beta jm xi xj sorry here, denote the corresponding subsequence of a ym such that the gamma 1m converges to be beta 1. By the same argument, suppose that the y1m has a subsequence y2m which is equal to be gamma 1 m x1 plus gamma 2 m x2 plus summation of a beta jm xj, for which the corresponding subsequence of scalars beta 2m converges, and let beta 2 denote its limit. And continuing in this way, after the n steps, we obtain a sequence ynm of ym whose terms are of the form ynm is equal to the summation of a gamma im xj, where summation of a gamma jm is equal to be 1 with scalars gamma jm satisfying the gamma jm converges to the beta j. Hence we have the ynm converges to be y, which is equal to be summation of a beta j xj, where the modulus of a beta j is equal to be 1, so that not all the beta j's can be 0. But since we have a sequence, we have a set x1, x2, so on xn is a linearly independent set, we thus have the y is not equal to be 0. On the other hand, the ynm converges to be 0 implies that norm over the ynm converges to be norm over y by the continuity of a norm. And since norm of a ym converges to 0 by our assumption, and the ynm is a subsequence of a ym, so the norm of ynm also converges to be 0. Hence, the norm of y is equal to be 0. But we already have that y is not equal to be 0, which is a contradiction. Hence, we get the result. So the next theorem will tell us about the relationship of completeness in a finite dimensional norm space. So every finite dimensional subspace of a norm space X is complete. In particular, every finite dimensional norm space is complete. We consider an arbitrary sequence ym in Y and show that it is a convergent in Y. The limit will be noted by Y, say. So we have this procedure, we will prove it out. If we will prove up this, that it is convergent in Y, so the space is complete. So it is given that the Y is a finite dimension. So suppose that dimension of Y is equal to be n and e1, e2, so on, en be the basis for the Y. Then for each ym has a unique representation of the form ym is equal to the summation of alpha jm ej. And since the sequence ym is a Cauchy sequence for every epsilon greater than 0 there is an n such that norm of a ym minus yr is less than epsilon, where mr is greater than n. So from this and the lemma, the previous lemma we have proved using up that lemma we have for some c greater than 0, epsilon is greater than norm of a ym minus yr, which is equal to be summation of alpha jm minus alpha j r ej, which is greater than equal to be c times summation of alpha jm minus the alpha j r, where m and r greater than n. So dividing by c, we have alpha jm minus alpha jr is less than equal to be summation of alpha jm minus alpha jr, which is less than epsilon by c for all m are greater than n. This shows that each of the n sequences alpha jm, which is equal to be alpha j1 and so on over the j from 1 to n is Cauchy in R or C. Hence it converges because here the R is complete, so it converges. So here the alpha jm converges to be alpha j, denote the limit. Using these n limits alpha 1, alpha 2, so on alpha n, we define the y, which is equal to be alpha 1 e1 plus so on alpha n en. And clearly here the y belongs to be a capital Y set. Furthermore, the norm of yn minus y is equal to be summation of a norm of a summation of alpha jm minus alpha j ej, which is less than equal to be summation of modulus of alpha jm alpha jr norm of ej. And as alpha jm converges to be alpha j, so we have a norm of ym minus y converges to be 0. That is the ym converges to be y. This shows that the ym is convergent in y. And since the sequence ym was an arbitrary Cauchy sequence in y, this proves that the y is complete. And this result, next result, we have already proved up in a metric space. A subspace M of a complete metric space X is itself complete if and only if the set M is closed in X. So using these two theorems, we have every finite dimensional subspace of a normed space is closed in X. And note that infinite dimensional subspace need not be closed or complete. For example, say that I consider up a set having a set of continuous real valued functions on the interval 0 1, and we define a norm as a modulus of xt where t belongs to be the interval 0 1 and y the span of x naught x1 and so on. where the xjt representing a t power j, so that y is a set of all the polynomials. That is, y is a span of a 1, t square, and so on, and y is a subset of a set of a closed real valued, continuous real valued function of the interval 0, 1. So here y is not closed, as the y and t is being representing as y 1 plus t square by 2 factorial, so on the t raised to power n over n factorial, which converges to be e raised to power t when n converges to be infinity. But this does not belong to a y, hence y is not complete. So thank you.